Today, most people find no strangeness in our concept that all matter is made up of atoms. Natural uranium is a mixture of two kinds of metallic atoms, uranium-238 and uranium-235. Most of these atoms are relatively stable uranium-238, or more simply, U-238. Only one of every 140 natural uranium atoms is of the richer or more excitable U-235. Both metals look exactly the same. In fact, they can't be separated chemically. Now, if one of the tiny wandering particles that we call neutrons happens to collide with an atom of U-238, it may simply bounce off, or it may be captured or absorbed into the atom. If, on the other hand, the neutron happens to hit a U-235 atom, it may split or fission the atom into several fragments. Part of the fissioning atom turns into pure energy, most of it appearing as heat, or in the form of powerful X-rays. In this release of energy, atomic power is born. The leftover pieces of the broken atom are called fission products. They are intensely radioactive and are now entirely different elements of lighter weight, no longer uranium of any kind. A very important part of the fission process is that the breaking atom throws out 2 or 3 of its own neutrons, each one of which may in turn hit and fission still another atom of U-235. Thus we may obtain a constantly increasing number of fissions. A chain reaction, the reactor people call it. And that brings us to reactors. In a reactor, we try to keep a chain reaction going at an even rather than increasing rate to give us a steady and controlled release of power. We can illustrate the basic reactor concept by starting with a simplified version of a reactor core. This may consist of a number of plates or rods of uranium metal called fuel elements, possibly enriched by addition of an extra percentage of the fissionable U-235, both for compactness and so that it will be easier to start and maintain a chain reaction. The core will be located inside of a tank or reactor vessel. And outside of it, we will want a heavy shield of metal or concrete to protect working personnel from radiation. Next, we will fill up the spaces between the uranium plates with water, graphite, paraffin, or any other material that will do a job that we call moderating. This moderator slows down the swiftly traveling neutrons to speeds at which they have the best chance of causing new fissions, rather than being captured by the U-238 atoms or bouncing off and finally escaping entirely. We selected water for the moderator in this simplified example because it also does such a good job as a coolant, transferring or carrying away the heat from the fissioning atoms. Now, with the water in place and the fuel elements correctly positioned, the reactor is ready. In fact, it would produce power much faster than we wish, except for one thing. We also insert in the core 1 or more control rods. These are normally filled with some material like cadmium or boron that will quickly absorb many of the increasing numbers of neutrons and subdue the fission chain reaction. As soon as we begin to pull the control rods out of the core, the rate of fissioning will again increase up to the level determined by the given rod adjustment. When the control rods hold the fission rate at just the right level, the reactor is critical with a sustained chain reaction. The steady release of heat makes the moderating water boil and give off steam. If we now cap the top of our reactor tank, we have a working steam boiler. We refer to this type of arrangement as a boiling water reactor. We can now pipe the steam off to drive a steam turbine and electrical generator, and we have a full-fledged electric power plant. A variation on this design is called a pressurized water reactor. In this, the cooling and moderating water is kept under high pressure so that it will not boil and turn into steam, even though it gets extremely hot. Circulating through a closed circuit, this water passes through a heat exchanger, like the coil in your hot water tank at home, and transfers heat to a completely separate second flow of water. Inside this second stage, the heat does produce steam to drive a turbine and generator. In some reactors, the moderator may be a solid, like graphite, and the coolant may be a substance other than water. Sometimes gas or even molten metal are circulated through the core to carry the heat to the heat exchanger. A great many variations are possible, but almost all power reactors use basically the same simple principles. However, the theoretical and engineering jobs that translate these principles into useful power are tremendously complex. Take, for instance, the uranium fuel elements of the reactors. Perhaps the fuel is used in the form of slim, plated, perfectly machined and polished rods. Perhaps the fuel is sandwiched between very thin sheets of protective metal called cladding, and then cut and welded into a precisely dimensioned rectangular grid, or some other machinist's nightmare. How enriched should the uranium be for best results? Shall the protective cladding be of aluminum, zirconium, stainless steel, or what? Sometimes the fuel does not consist of metallic uranium at all, but of a ceramic form, uranium oxide, again possibly in metal-clad plates, rods, or even small pellets, and so on. It is possible to wring scores of changes on this solid fuel question alone, and each and every good idea must be tested before being used in an operating reactor. Similarly, the coolants must be tested, the moderators, the heat exchange methods and materials, and 1,001 other items, first as experiments in test reactors and later as part of reactor prototypes themselves.